Hello, everyone, and welcome to this week's SMaRT seminar series. This is a joint seminar series between Johns Hopkins University in the United States and Indian Institute of Technology, Delhi in India. And today it's my pleasure to host Tapas Tripura, who's a researcher in computational mechanics and scientific machine learning. He obtained his undergraduate degree in civil engineering from NERIST and his master's in structural engineering from IIT Guwahati. He's currently pursuing his Ph.D. in the Department of Applied Mathematics, Mechanics in IIT Delhi. And at IIT Delhi, he's also affiliated with the Center of Scientific Computing and Computational Mechanics. His research lies at the intersection of physics, computation, and AI, and he's being advised by Professor Shovik Chakraborty. His current work focuses on data-driven discovery of physical systems, operator learning, scientific foundation modeling, and reinforcement learning for intelligent control of mechanical systems. He has also introduced the idea of wavelet neural operator and has proposed the Lagrangian discovery framework for uncovering governing equations directly from data. He has numerous other accolades, one of them being obtaining the prestigious Prime Minister's Research Fellowship Award from the Ministry of Education, Government of India. Now, with that brief introduction, I would leave the floor to Tapush for giving us this insightful talk. So it's all yours.
Yeah. Yes. Thank you. Thank you so much for this brief introduction. So, I'm really actually glad to have this opportunity to present a part of my doctoral thesis work in the SMaRT seminar series. So, specifically, I'll be talking about this model-agnostic predictive temporal difference algorithm for deep reinforcement learning of systems with either partially known or completely unknown physics. Yeah. So now, before directly jumping into the details of how MapTD enables that predictive control, I would like to take a brief moment to set the motivation. So now, if it is actually needless to say that the goal in engineering is to model, analyze, and design of complex systems to meet our requirements. However, once these systems are deployed in real life, so we expect them to continually perform we perform in terms of either stability or reliability. So again, these engineering systems are often subjected by external events like extreme natural events or environmental forces. So now to to set this problem, so I will consider two examples that capture this idea. So on the left, you can see there is a example from structural engineering, specifically a tall structure subjected to wind force, where we should ensure that the wind-induced vibration in the tall skyscraper not only introduce in discomfort to the users, but more importantly, do not cause fatigue or damage of structural components. Again, on the right, I have an example, specifically the flow around an aerofoil. So here, the wind flow near these sharp edges sometimes form these vortices, so which introduces vibrations to the aircraft structure. So now, these examples highlight that this maintain the desired performance, basically to maintain the safety, stability, and their reliability under this evolving uncertain environment conditions and this real world dynamics. We need strategies that keep their performance intact. So one of the way to keep their to sustain their performance is the active control. So now, if we move forward, that active control is not something that is very new. It has been there for decades. So the popular ones, maybe the PID based controller or this linear quadratic regulator based controllers or H infinity controllers, or in fact this most robust that MPC, that model predictive control. So now, however, all of them suffer from some fundamental drawbacks. Like these regulators or these controllers, they assume that, or basically they assume a precise mathematical model of the underlying environment. So if we like try to like see real life engineering system or real life structures, the precise mathematical model of them are never available. And in fact, obtaining a like precise mathematical model for them is even impossible or intractable. Now again, this like controllers like this PID and LQL, they assume they are based on this they linear approximations, so they cannot handle this hard strong nonlinearities. Now there are other issues like this MPC and H infinity controllers. They like they do robust control, but there is a trade-off between performance and robustness. If we want them to give real life online inference, they become they like their robustness decreases, and if we improve their robustness, the computational cost associated with them increases. Then another issue is that scalability. And finally, that if we go to that most like flexible one, the model predictive control, they are limited by the fact that they use an online optimization for deriving these optimal control actions. So which we cannot, which is actually very expensive in the like in the view of this online like real-time control. So now this basically motivates the need for an policy theory control schemes like deep reinforcement learning. Now, if we will like start with an environment. So like for a mechanical engineer, I'll visualize environment as a cantilever beam, say subjected to an uniformly distributed load, or could be a point load also, and augmented with an piezoelectric patch at some part of that beam, so which will act as an actuator. So now if we go back to the very that like classical like form of deep reinforcement learning, that is basically the model free reinforcement learning algorithms. They act, they provide an action, say for in this case this through this piezoelectric patch to the environment, and with that interaction it gathers some experiences, basically the states, and then with that experience it finds in policy to finds in policy to get rewards from future actions. Now there is an issue. Now here the issue is it since it gathers experience through action, it tends to become sample inefficient. So basically, it needs very huge number of training episodes or trial and error interactions with the environment to learn an effective policy. Now, this model-based RL like tends to or like overcome this limitation by introducing an like model of the underlying environment. And then with that model, it does planning at each time step t, thereby eliminating the need for like frequent trial and error interactions with the environment to derive an effective policy. Now, again, there is an issue with this present deep reinforcement, like model-based deep reinforcement learning strategies. Like here, actually, the policies are learned simultaneously with the that underlying model, underlying surrogate model. So now just assume that if the policy goes wrong, the model that is also learned through these interactions also will become corrupted. And you will realize that as your prediction or this action like goes towards long horizon, your that corrupted model, the chances of corrupted model to like also corrupt the policy increases. So with that, like this framework, basically this MapTD aims to develop a like a model. Basically, it aims to like symbiotically combine that model discovery and the temporal difference-based reinforcement learning to eliminate the what you call limitation of this existing model-based reinforcement learning algorithm. So now before like diving into again this MapTD, I would like to set certain key terminologies for the audiences. So I'll start with this environment. Again, this is for our case, maybe this cantilever beam. And then we have an agent. So for our case, this is in this piezoelectric patch. So which gets to measure its position in the environment through these observations. So in our case, this is basically displacement, velocity, or acceleration. And then it gets to take an action following some policy pi such that it maximizes the reward. Okay. So in this case, the reward is you can visualize it as a numerical feedback of the action taken by this agent towards this like reducing like to the like basically it's a measure of how that action has successfully or or it didn't become successful to reduce the vertical displacement of this cantilever beam. So now in reinforcement learning, these are often modeled as a Markov decision process. So represented by this tuple of this continuous state space S and continuous action space A and a transition function G, a reward function R, and a discounting factor gamma. So discounting factor is basically a real number between 0 to 1, which basically tells you how much do you favor getting an immediate return at the current time step versus your future returns. So basically it discounts your or gives importance of your like actions at this future like time steps. So now at the end of the day, our aim is to learn a policy pi. Now the issue is in reinforcement learning, the policy pi is often not often, it is always a probabilistic. And due to its nature, learning that optimization of this policy becomes very hard. So in that case, we want to learn that or maybe parameters the policy using neural network. Since neural networks are very good at learning very complex functions, we also want to take that motivation and learn our policy as a neural network or as a parameterized model. Now towards learning this policy pi, like how do we judge like which policy is good? So this is done using a value function. Now being a state S, if we sum all the returns from the future, like basically those rewards from the future, like it is that value function is defined as nothing but the expected rate of return. Now, if we start from that state S and act on the policy pi. Okay, so now again, now this in model free based RL, this value function is maximized by performing an optimal that optimization over an that complete horizon. So basically, so that's why it needs multiple that episodes or basically trial and error interactions environment. Now in MapTD, as the name suggests, this like it is a model-agnostic predictive temporal difference. So we want to introduce certain kind of planning, which will like avoid optimization over this complete horizon. So that's why we use this like MPC policy. So this is motivated from the classical MPC family of algorithm, where we estimate this expected rate of return over an horizon H, and then derive an action sequence A, which has a length of H, which is optimal only up to that horizon H, and then we'll apply only the first action. Now again, there is an issue. Now predicting, since we are not now relying on this trial and error interactions with environment, so basically given the present state ST, we want the transition function or basically a dynamical model, which will give us predict the future states over the horizon H. Now, again, we don't want to go back to that like classical MPC scheme where we have to either rely on simplifying assumptions or neither the existing model-based deep reinforcement learning algorithm, where we have a chance that our learned model will be corrupted by these wrong policies. So in that case, our another aim is to learn a uh, model, possibly a parsimonious one, but a generalizable over long horizon. Okay. So now to summarize, so we have let's consider time axis t and some reference. So in the case of cantilever beam, this will be an ideal condition if there is no vibration, no like vertical deflection at all. So and then we at the current time step t, we have some measured input and some past control sequence. Then we set a at the present time t, we consider prediction horizon h. We randomly generate some optimal action, like not optimal, some action. And then based on this transition model, this G, we predict this state possible and then minimize the difference between the reference and the state, the trajectory, and which will ultimately yield the optimal action sequences over the horizon edge. Now, once the optimal action sequence is derived, we'll apply the first action sequence and we'll move to the next time step. Again, consider the horizon and we'll move forward. So now, so at this stage, we'll detangle our this objective. The first part in the first part, we'll focus on how to learn and interpret or maybe generalizable, possibly a parsimonious one, parsimonious model for this underlying governing physics, so that even a system whose physics is partially known or completely unknown, we can discover we can either discover or correct the like known physics. And then in the second phase, we'll like go on like I will try to show how to learn this policy pi using this learn physics G. So now we'll assume that our this governing physics can be represented by this first order dynamics. Now, where our aim is to learn this that function G, basically the dynamical function G, from an noisy observations of these states. Now, now how to do that? So to able to like basically derive this G in their parsimonious and interpretable forms, we'll represent this G in terms of certain candidate functions. So these candidate functions are represented here by this var epsilon and their parameters, like weights of these basis functions given by this theta. Now, if we arrange with some little mathematical manipulation, so we'll obtain with this regression equation. So now, if we like to summarize, we have some data, and given the data, we'll construct an dictionary function D, which will contain certain interpretable basis functions. So this interpretable basis functions could be that polynomials or this harmonics, their difference, and their partial derivatives, anything you can possibly like can include it. So then we perform regression to identify our that governing physics. Now, since we have noisy observations, it is always good to have a probabilistic model, which is basically the aim of the sparse Bayesian learning. So in sparse Bayesian learning, again, our aim is to find the posterior over the model parameters theta, rather than their exact like their deterministic values. So now this posterior is found, basically it is found by multiplying this likelihood over some prior and with some normalizing constant. So in the absence of this normalizing constant, this posterior is proportional to that likelihood multiplied by this prior. Now, since as compared to this least square methods, we don't want all the basis function to be present in our final model, or basically to overcome this overfitting issue, we like we we'll try to promote some sparsity in this model. So that sparsity in this setup, in this SBR setup, is promoted through this prior p theta. So for our case, we'll consider this discrete spike and slope prior, which is not a like basically a composite distribution function involving a slab represented by this Gaussian distribution and a spike which is represented by this Dirac delta function. Now the spike and slab some extra parameters like this Vs, basically denoting this slab distribution, a pattern indicator variable z, which takes either 0 or 1. So it basically tells you that theta, that basis function, whether it corresponds to slab or spike. So now if we do some mathematical manipulation, we can find our posterior distribution in this form. Again, that analytical solution to this is not available. So we have to resort to some MCMC-based sampling scheme. So now if we do sampling and remove the initial burn-in samples, and we can calculate this marginal posterior inclusion probabilities. Okay, so this actually tells you like probability of each basis function being present in the true model. So now to derive the final parsimonious model, we'll select a threshold PM and threshold PM, and all those basis functions whose MP values are less than this PM will discard them. So ultimately, if we then translate them in this matrix that vector form, so our this learned parsimonious model will be represented by this d theta. So d will have this predefined candidate basis function, and theta will be that a sparse set of sparse vector representing only the most important that candidate functions. Okay. So now with this, we will be now at this stage we'll have with this we'll derive this that predictable model. So now once this predictable model is available, we'll now move forward for learning the policy. Now to do that, we'll consider a multivariate Gaussian distribution over this action sequence. We'll assume that our control vector has d elements, so that our this a will be then our that a will be sampled from a multivariate Gaussian distribution with d variables. We'll also assume then these action variables are independent from each other for simplicity. So with that, we'll sample any sequence of any sequence of this action. So each each trajectory in this any sequence will look like a matrix of dimension small d cross h, where d is the number of control variables or basically the actions a, and h is that horizon, the dimension of the horizon. So now with that, we'll pass it all the actions to the environment, which contains our that learned model G, which will give us the set of observations S for all the all the trajectories in this any sequence, and then we'll estimate this expected return over each trajectory in this any sequence. So now if you see this total expected return, this is nothing but the value function we have already introduced. So this is basically nothing but this expected rate of summation of all the this is returns from the future. Now here in this red term, there is a new this is a new term which was not present in the value function. So this represents a the terminal cost estimated by this terminal function q theta. So this basically tells that at the end of each horizon, I want to reach to some final value, and if I don't reach there, I will have a cost to pay. Again, this learning this terminal function is intractable. So we'll also try to learn this terminal function simultaneously with our policy pi. So learning this policy has two components now, learning this Q function and this pi. So if I represent theta in pi, this policy, that will include both. So now once this expected return from all the any trajectories are obtained, we'll select top n trajectories with the highest returns. So we call them elites. So we'll select top n elites and then use cross entropy method based scheme to update our this action distribution. So now here these weights phi, they like resemblance the Boltzmann weight from this Boltzmann distribution. Now this is only one iteration. Now with this updated mu and sigma, we can again generate some that any sequence from this updated multivariate distribution and uh, continue it for j number of iterations, so that after j number of iterations we'll have an converse distribution. At least we can assume that it will be converged. So now again here it doesn't involve any policy network pi. So in the next step, so what we'll do, we'll for like during this sampling of this action sequence, we'll also sample an n pi number of action sequences from this policy network. Now to introduce stochasticity, we'll add some small Gaussian noise to those n pi action sequences sampled from this policy network. And over this n pi number of action sequence, we again will calculate that we'll again pass it to the environment and find the corresponding observations. So we'll have now NE samples from this that multi-bit Gaussian distribution and n pi number of samples from this policy network. Now, obviously, at the beginning, that policy network won't be optimized. So in that case, but as the training at each episode goes on, this policy pi network, this pi will be we'll try to approximate the true or the optimal policy pi. So in that case, the contribution from this policy network will come into picture. So now at each episode, we'll store our this state action Q and the next state, the tuple of these four quantities in a replay buffer. So at each episode, once it is stored, so in the beginning of the next episode, what we will do, we'll sample a tuple of this as that state at present and next, then action at present, and that Q values from this present time t, and then use an agent to predict the next step, basically the policy which is updated from in the previous episode to predict an action A. So now this action won't be optimal, but still we'll find that the corresponding Q values, and using environment we'll predict the next state, and then we'll estimate a one-step cost function, which is nothing but the norm between these Q values, which we gathered from our that multivariate like from this replay buffer, and then basic difference between this Q value and a Q target. So Q target is represented here by this Q star. So that is computed by that R, the rewarded present time plus discounted that Q value from the next step. Okay, so here in case you wonder what is this Q theta minus represents, this is basically a moving average copy of our Q network, this Q. So now if I sum this one-step cost function over the horizon H, and then I can use any gradient-based scheme to update the parameters of my this agent. Okay, so with that, like at one episode, like at each episode, I will also update my this like policy that policy network. Okay, so now another thing is that like once like for generating these trajectories in that horizon, we use an high fidelity solver. So like what we observe that solely relying on this high fidelity solver for like running this policy increases the training time by a huge amount. So like then we like wondered what if we like augment this high fidelity solver with a neural operator. So basically that's why we trained a neural operator on this discovered dynamics. Basically it is pre-trained, and then we used it alongside with the high fidelity solver like in an intermediate alternative episodes to accelerate our training. So this is called sim to real based learning. Okay. So now to summarize this map theory framework, we have environment. So we'll gather some observation. We'll try to discover either the partially known or the completely unknown physics using this SBL. Then we'll pre-train a neural operator. Once these two things are ready, then we'll deploy our map theory agents, which will use this that NFEM or high fidelity solver for this like discovered model, and the surrogate neural operator for prediction. Then what happens given the observation using these solvers, it like predicts and finds some action sequences, and over that any plus n pi number of action sequences, over that we will use our Q network to find the Q value, basically the Q values or the quality of each action. Now only those the basically the top action with the highest reward and highest value will use it as a action to the environment, and this will complete our that feedback loop. So now if we like once this model is trained, so like it can be used for like situations where like environment is like partially or completely unknown. Okay, so with that, we'll consider the first example, again, that cantilever beam, where it is subjected to uniformly distributed load. It has a piezoelectric patch at the distance of 1/8 to 0.5 from the left support, the fixed support. And here we assume that the physics of this cantilever beam is not available to us in a priori. So although we assume that, but for generating synthetic data for comparison, we use an Euler-Bandoli theory. So ultimately, the governing control equation is given in this form. So here we have that discovered model represented in the form of d theta. We have an external disturbance F, and we have an control action to be provided, this A. So we use this reward function. So if you see, the reward function has this negative, it is like all the quantities are negative in this reward function. So it basically says that if the more the discrepancy, I'll give the less reward. And similarly, the green term in this action, it basically regularizes the action sequences by so it actually um, like avoids taking very large values of action. And this delta A term represented this blue, so it actually regulates like drastical change of action in the like consecutive time step. So now with this, assuming that the model is unknown to us, we have like tried discovering the governing physics of this cantilever beam. So here the model inclusion probability, the marginal posterior inclusion probabilities after discarding those abundant samples are presented. So we had almost around 19 basis functions, so candidate functions. So among that, you will see only the candidate function, that fourth order derivative, has an that MP value greater than this 0.5. So 0.5 is our threshold. So now in this subplot B, we have shown you I have shown that probability density of this identified basis, that basically the fourth order derivative basis. So you'll see the mean almost exactly matches the true mean. So if I to translate it in terms of equation, you'll see the discovered model preserves all the not all the only basis functions present in this true model with very negligible like error in this parameter. So now here we have carried out the training for around 1,000 like 1 lakh environment steps. So near this 1 lakh environment steps, we found that it almost converges to the total cumulative return from this NPC. And for a comparison, we have also considered an like existing TD-MPC algorithm, which also uses TD-MPC plus MPC-based like this framework for model predictive control in deep reinforcement learning. You can see that although our MapTD has able to asymptotically converge to this baseline MPC, that TD-MPC has actually failed to improve its policy. So now this can be visualized in this in this GIF. So here I've shown this responses from like basically there are responses from 4 cases. The gray one corresponds to the response without control. The green one is the control response from this baseline MPC, and similarly these blue and red ones represent the control responses from the existing TD-MPC and the proposed MapTD. The dotted lines here show like indicates the target bound. So basically, I want to limit my the vibration of this cantilever beam within this target bound. So now you will see that that performance of this TD-MPC is almost similar to without control. So like whereas you will see again that MPC it almost achieves a uh, stationary position after some time. So which is again basically very impracticable from the real point of view because there will always be some residual vibrations. Now, if you see our this map TD, you'll see there are certain very minor violations of this target bound, but still after a period of 0.5 seconds, it almost tries to regulate the vibration of this cantilever beam within the target bound. And okay, so now the significant acceleration, what we like, or maybe the significant contribution of this MapTD is in terms of this inference time. Now in MPC, we observed that per planning horizon, it takes around 38 seconds. Now imagine if you were to deploy an MPC-based controller in real time, like you cannot actually do with that 38 seconds of planning, right? Now, on the other hand, TD-MPC takes the smallest one, if I remember, around 1 millisecond. So, but again, you see, although being first, its performance nowhere near this either baseline MPC or the proposed MapTD, or maybe nowhere near the target bound. Now, on the other hand, this MapTD, it achieves an computational or computational like acceleration of 2.5 into 10 to the power 3 times than the base NPC. But it with even with that computational acceleration, it almost matches the performance of this like the baseline NPC. So it is safe to say that this MapTD like strikes a balance between this computational acceleration, like basically the inference time and its controlling performance. Okay, in the second example, we considered a very large example. So, which is 76-degree feet of benchmark structure for active control. So, in its in the true form, it doesn't have any linear non-linearity. It is basically a linear structure. So, what we did, we artificially adapted this benchmark by adding non-linearities in 3 flow. So basically, this actually resembles a practical scenario where due to like degradation or maybe some operating changes, the like non-linearities are introduced in some of these fluids. Okay. So now the properties are mentioned here. We again consider same reward function. So if there is a discrepancy between this displacement and velocity from the target bound, we'll penalize it. If again, while optimizing this action, we don't want the actions to be very big value. So we are regularizing with this norm over this A, those action variables. And we also don't want drastic change in action values at subsequent time steps. So that is like controlled by using this normalizing factor, this delta A, norm over this delta A. So again, we did the same comparison. So here we observed that with 40,000 after 40,000 endpoint steps, there is no further improvement in the policy. So we decided to train it only for 40,000 environment episodes. So not episodes, 40,000 environment steps. So like you can see at the end of this 40,000 environment steps, the MapTD is the cumulative data from MapTD almost asymptotically converges to this Bayesian MPC. It doesn't touch though. But on the other hand, this TD-MPC, like although it shows steady improvement, but after 200 environment steps, it almost stagnated. So the performance can again be seen in this GIF. So here again, the evolution of trajectories for 4 cases are shown. The blue one is without control. The dotted black ones are the controlled trajectory from MPC. The red dash dot, that graph is from indicates the response from this MapTD, and the green that dotted bar that represents our the target bound. So now here it is basically if you observe this displacement, you will see like all the controlled trajectories from MPC, TD-MPC, and MapTD, they fail to satisfy or lie within this target bound. But you see the performance of MapTD, it closely follows the results from this MPC. So now if you observe this in terms of this, if you observe this velocity response, you will see the MapTD and MPC, they were able to optimize the velocity responses within the target bound with uh, like uh, like infrequent these violations. However, on the other hand, this TD-MPC, it almost acted like this with like no control response. So despite being these challenges of this tall and flexible structure, this MapTD, it to some extent it is able to regulate the uh, responses within this target bound, and also like followed an optimal like control derived from this MPC. So this signifies that MPC, this our MapTD, can be actually implemented in real life scenarios. So now again, in terms of this the inference time, like our MapTD takes around 0.07 seconds per planning horizon, whereas this TD-MPC takes around 1100 seconds per planning horizon. So which is very huge considering real-time control. Obviously, TD-MPC obtains the lowest time of 1 millisecond, but its performance is again very poor. So now the third example I have considered an example from fluid mechanics. So where the situation is, I have a rectangle channel, a rectangle open channel. So I have a circular cylinder in the middle. So when the flow, I have applied a uniform flow. So when the flow meets the circular cylinder, it basically introduces vortices. So basically known as the carbon vortex streets. So those carbon vortex streets basically gives rise to elevated drag and fluctuating this lift coefficients. Now those elevated drags, sometimes they introduce like scour or like even like increase increase decreases the efficiency of this engineering system. So my aim is to reduce the for like basically weaken the formation of those carbon vortex streets with the help of two synthetic jets. So those location of those two synthetic jets represent in this red circle. Now those synthetic jets are controlled by a MapTD agent, where specifically the MapTD agent controls two parameters. So one is this actuation frequency, and another is this actuation velocity. So now we with that aim, with that motivation, the aim is to map the states, basically the velocity, the field to the corresponding forcing frequency and the velocity, the jet velocity. So now to reflect the effect of action or to effect of action on the drag and lift coefficient, we have designed this reward function in this manner, where we are like penalizing uh, the reward function for more like increasing lift and drag coefficient. So we are saying that if there is more drag and lift, so it will give less reward, and if the drag and lift is less, then there will be more higher reward. And similarly, we have an regularization over this action, so such that it doesn't take any significant like very large amount of these values. So again, here we assume that we don't have any clue about the flow model. Like, so we with that aim, we first tasked the MapTD to identify the governing physics. So here we again had this 19 basis functions. So now here, due to the very fluctuation in this flow field, we have set a higher that target and that threshold empiric value. So to be specifically 0.7, you'll see only 5 basis functions out of this total 19 bases are like that actually has a empiric value higher than that our threshold. So now if we translate into the equation form, you'll see the discovered model preserves all the basis functions of the true model. And on top of that, it also identified the overall model with like negligible like discrepancy in this parameter identification. So now we again have again illustrated this episode related and inference time, which tells uh, that basically like I think we have performed around 45,000, 45, 4 lakh 55, 4 lakh 50,000 like employment steps to like optimize our policy. And then if we look at the inference time, the story is not different from the previous case, whereas this MPC takes a very high amount of that planning time per the step. MapTD takes around this point 0.9 seconds around per planning per horizon step to plan an optimal action. Now the result in terms of this optimized trajectory is displayed here. So you see that without control, the flow field shows that like formation of these permanent vortex streets. Whereas once the MapTD is tasked to control the flow, we observe and very well behaved streamlined flow. Now to check its performance uh, in in the in terms of drag and lift coefficients, we have also tried plotting these drag coefficients and their power spectral densities. Now, if you see the top two graph, you'll see after a transient period, so basically only that first maybe first 1,000 enrollment steps, the CD values of that control response, basically that blue graph, it is very like low, significantly low from that without control. This is not different from lift, and again we see that the lift coefficient and the control flow is very much zero. Now again, the Ph.D. the power spectral density of this drag and lift coefficient again tells the same thing. So we see that the energy content in this that dragon lift coefficient in the control flow is much more less than the flow without control. Now in the next step, we went a little bit ahead and tried like applying that learned policy in a different geometry, where basically that block body where we trained had a circular geometry. In this case, our that block body has a square geometry. So with that, that to uh, to create and synchronization, we also like basically we maintained the same that dimension geometry, basically the flow geometry, same as that circular cylinder. Basically, the number of gradient are all were kept same. So only the thing changed was that circular cylinder, this square cylinder, and whereas in the previous case that jet had was symmetrically placed on the up and top of the cylinder, here it is placed in the trailing edge of the square cylinder, again symmetrically on the top and bottom. So then we again applied the trained, basically the pre-trained that policy from that circular cylinder, and in this case, and it was very shocking to observe that like it in this case also, even without training, it could generalize to some extent. So basically, this underscores the effect of planning, in that policy. So with that, like I will end by this presentation here. So the paper is currently under review. So the code, once the paper is published or accepted, will be uploading. So meanwhile, the model discovery and the neural operator used in this framework, you can see it, you can access it from these links. And if this work excites you, you can also go and visit other exciting works in my website or in my GitHub repository. Yeah, so with that, I will conclude this and my presentation.
Thank you so much, Taposh. This was wonderful. Before I I ask questions, I was wondering if there's anyone in the audience who wants to start. Yes, Tabakar.
Hi, Tapas. It was a very
Yeah, hi, Deepak.
wonderful presentation. Thank you for sharing. I had a couple of questions.
Yes.
First, if you could you please go to the slide where you show the replay buffer? Uh,
Okay. Yeah,
the
this one.
yeah, this one.
Yeah.
Here, if you see, you are collecting the Q also, right?
Yes.
So, like just a maybe silly question, like if we have a queue in our data set itself, then why can't we just maximize over the queue and just get the action instead of
Uh,
to,
yes. So basically, here, this queue we had right in this network, in this
mm,
file. So that is also not known to us, basically. So we also, basically, that is actually a common thing to do in reinforcement learning. So we actually don't exactly know what is this queue values. So here,
mm.
we just collect this queue and we like basically try to update it asymptotically in all the episodes. So like maybe okay, so maybe I think this is what you wanted. So in the replay buffer, whatever the queue we are collecting, so this is also not optimal. So in the initial episodes, it will be wrong, but with that wrong estimate, we try with that maximizing reward, we try to uh, improve our this queue, and that will give me the queue values, and it will go in that circle.
Oh, so these are the approximated queue that you are collecting,
Yes,
not the real
it
queue.
is an approximated from previous episode. Then with that,
I
it
see.
will because basically we don't have any queue, basically no level here in this, in this set.
Yes. Okay. Yeah. Thank you. And
Yeah.
I have
Okay. Yes.
as another question. I know this
Yes.
work cannot be comparable to some kind of a model-based reinforcement learning because you are also discovering the physics, basically.
Yes.
But let's say we know the physics, and if we use a model-based reinforcement learning, should we expect similar results with this?
If you assume that the model is it is exact to your real system, yeah, I believe that that will give you better result than this.
No, like maybe some kind of a, like a Dreamer V3, where we use transformer to just approximate the states, something like which is very similar to what you are doing. You are learning the environment from WNO, and then using its inference to learn the actions, right?
Okay, so basically you want to model those, basically learn the underlying model using some deep neural network or say some
Mhm,
surrogate model.
mhm,
So actually, in the previous literature, it has been seen that they actually do good in short horizon, but if you go towards that long horizons, they actually suffer from this that issue, that generalizing issue. And so basically that TDMPC, which I have used for comparison, they also do it, but they learn it in the latent dimension, where they argue that in robotics, basically, if you take a picture of this robot, those shades, shadow and all those things actually doesn't matter. Only matter is the joint angles and all. But in our case, since in our this beam or this flow here, even those shade basically in the vortex shades, even those shades have some meaning. Basically, the difference in pressure gradient and all. So I don't know if sacrificing those are really important. So maybe that's why in that result I have compared with TDMPC, it actually failed miserably.
I see, I see. Okay, maybe another two question if time permits.
Go ahead,
Can
Tabakar. Yeah,
yeah.
go ahead.
So one just a very just a thought that if you are approximating the model itself, and since you are learning with WNO, what differentiate optimization and learn the action.
We lost you.
Hello.
We lost you.
Yes.
Uh, Sorry, am I audible now?
Yeah.
Yeah, I was just asking that since you're learning the surrogate, neural operator surrogate, and it is differentiable, why can't you just do a like a differentiable optimization to learn the action sequences?
Uh,
Like they just frame a simple optimization problem instead of learning, like go the RL route.
okay, so you want to say that this basically neural operator, I will have some neural operator, maybe neural network surrogate. So I'll give the
Mhm.
state and I'll predict action, something like that.
So the neural operator, yes, yes, exactly. That's what neural operator or surrogate will predict the states. And since it is a function of action, we can just evaluate the action using some gradients. That like
Uh,
just a thought.
yes, but then from where like we'll get those action level. So that action we have to generate from some algorithm, right?
Uh, yeah, we can parameterize the action, like maybe some neural network, and learn the weights of the neural network.
So you have a neural network surrogate,
Mhm.
so which basically takes action and state as an input and gives you the next state.
Mhm.
So actually in this case also that this tailor operator task is that only. So it basically takes action and state and gives you the next state, but that next state is only used for prediction.
Just to follow up on Dibakar's question, is it like you are giving the initial condition and you're predicting the entire series and you're just picking up the next time step and doing your model learning?
Okay, that step one, right? So no, here actually it involves it involves no reinforcement learning part. So where what we do, we environment is there. So basically just an environment is there. We just collect a single like one step data. So basically say first 2 seconds, we just simulate one single realization. And then over that we derive our model. So it has nothing to do with policy learning. So it is totally detangled. And then over that we train a neural operator just as a like predictor. So that will help to accelerate the training. So even if we don't have this neural operator, so it will work. If we can solve this data-driven, this discovered model using any FEM, AVM, anything. So once this is done, so then we continue training or predicting. So these are totally detangled. Is it what you wanted?
Okay.
Yeah, I think, yeah, thank you so much for answering the questions. Thank you.
Okay. Jay, you have some questions? I see you raised your hand.
Yeah. Thank you for the presentation, Tapash. I had
Hi,
questions. Yeah. So for your baseline model, was the next state for your action like known, or was it also learned?
For your baseline model. So during this comparison, are you talking about?
Yes.
Baseline MPC is my next step. No. So baseline MPC, we just run this plain MPC where we assume that that true physics is already known. So there is no discovery. There we as it is use our that exact beam equation, and we optimize at each instant of time using this LV here that LVFGS. Yeah. So and then we optimize that action, and based on that action, we again feed it to the actual environment, basically the beam equation, and we solve it. So there is no approximation.
I see. So like it's fully known in your baseline's case.
Yes.
Okay. And then in reinforcement learning, usually with probabilistic approaches, they
Yes.
tend to suffer with increased space in state space and action space in terms of computation times. So like when we increase the number of states, number of actions, the model's taking a lot longer to train, or it degenerates the performance because it makes more assumptions. Was it something that was explored within your case, or?
Yeah, that part I didn't. Yeah, that part I didn't explore. Yes. Yeah, that's a good point. Yeah, I see that. But I think that's also kind of obvious in this case. Here we had approximately our state, what this beam was discretized around 256 grid points. So like I think we successfully done the training within this one lakh training episodes, whereas in that last example in this case where we had this very big grid, so in that case we took almost like 4.5 lakh of training with environment steps. So another one thing we have done is we assumed like in this case, what if instead of having this full flow field, we have only partial observations at certain locations. So certain velocity probe locations. So we had around that 147, but in terms of performance, we didn't see much degradation. But obviously, that computational part that was overlooked from my side. But yeah, I'll explore it.
Thank you.
Okay. We can take one last question from Vishwa.
Yes, Tripura, it is great presentations, and it is interesting as well. So I have just quick questions. So basically, you are using DRL to predict this flow over valve body kind of problem. So are equal to how
Yes.
much you are able to predict this model?
Okay, so these results are shown for RE300, and I think we went up to 500. Yeah, so beyond 500, we didn't try.
Up to 500, you are able to predict, huh?
In 500, we able to control it, but obviously that performance was not as good as this 300 or 400.
Okay, okay. So what about this model, the chaotic system like turbulent flow kind of thing? So have you tested in turbulent kind of scenario?
Actually, yeah, that
I
we
mean,
didn't go to that.
I mean
Yes.
higher value, bigger than 1000. So have you tested that?
No, because we didn't go to that supercritical flow. So we are in kind of this 300 to 500, basically in the like just beginning of that turbulent region.
Okay, okay, okay. For
So basically
observation.
there was a paper like I think it was in JFM. They considered only 100, so we just extended it to 300 and 300 to 500. Yes.
Okay, okay, okay. That's fine. So for this inference data, you are using WNO data.
Sorry.
For inference experimental purpose, data-driven purpose, you are using WNO to surrogate this WNO neural operator for surrogating this model, na?
Yes. So basically, I have an LBM based solver. So say assume that half of the episodes the LBM runs and half of the episodes the WNO runs. So they are kind of intermediate. So if there is any discrepancy in this WNO,
Yes.
so that LBM will not let the discrepancy propagate to the policy.
Okay. That's interesting. Oh, yeah. And one last question, my side. So, how much snapshot you have able to predict, and how much data you're using for training purpose and testing purpose? How much snapshot data?
Which example?
Flow per circular cylinder.
Okay. So actually, we have did the control till I think 20,000 LBM steps, and then we predicted till 40,000 LBM steps. So beyond that, we actually didn't explore it. So I'm not quite sure whether it will perform or not.
Okay, for training purpose, you are using whole snapshot data or some snapshot randomly you are picking.
No, we have considered two sets, two studies. So in one study, we assume that we have this full flow field data, and in another a case study, we considered some 151 velocity probes. So basically, the 150 that points around the circular cylinder.
Okay. So interesting it is. Okay. Thank you.
Yeah, thank you.
Great. Tapush, I guess you already know that you've made a wonderful presentation. You've generated so much of interaction across the audience. So, yes, thank you so much for this wonderful presentation and presenting it to the Smart Seminar series. With that, we'll close today's session. There's a small announcement that we wanted to make today which is specifically for the Indian audience. So for the Indian, because we had a daylight change, which has changed our timings. So for all the Indian audience, instead of hosting this at 7:30 p.m. on Wednesdays, we will have it on at 8:30 p.m. on Wednesdays. And that would keep all the US and the European time zones intact. Okay. So with that, thank you so much. And we look forward to seeing you all in the next session. Thank you.
Thank you.